Hey guys, this is Chemistry for Faith and this is the video for April 24th, and we're starting chapter 16. So what you all should have been doing this past week is that you received a test on chapter 15, which is over acid, bases, and salts. I did not do another video this week after Tuesday, I guess, because I was letting you have a couple of days to try to search like mad people through your book and through your notes, hopefully, to do your test. So today we're starting chapter 16. Chapter 16 is over oxidation reduction reactions in electrochemistry. If you were here, we would try to make a voltaic cell battery and do some other well, actually, I mean, it sounds pretty cool, but it's not. It's actually we would put a bunch of nails in acid and watch it rust, which, this corrosion process. But this is a short chapter. It's supposed to be combined, weird hair, it's supposed to be combined with chapter 17, which is on nuclear chemistry. Your last chapter, chapter 18, I talked about this earlier, is over organic chemistry. So, this is your last week of chemistry. Chemistry ends May 1st, and you technically only have one more grade, which is a quiz over chapter 16. So we'll go over it. We'll go over not last week. Next Friday, May 1st, will be your last day of chemistry. And the only reason that's your last day, the nuclear chapter is really long. We probably wouldn't be able to get through it. Also, it's because you guys are upperclassmen. Thanks to Carrie Grace and Isaac. Carrie Grace is graduating, so she has to get through her stuff quicker. And so Mr. Clark said we could just end chemistry of chapter 16. Before you think you're being cheated, chapter 15, just going by my notes, and I don't even think people got through chapter 14, to be honest, or chapter 12 and 13, to be honest, just looking at notes. We've probably gone farther through this chemistry book than any previous class. And we've done far more labs and probably, done a lot of stuff. So don't feel like you've been cheated. We've actually probably gone farther than a lot of people have that were using the original videos. So we're starting today on a new chapter. And it's kind of sad because, you're starting on your last chapter. But I would look through the nuclear chemistry chapter. That I thought was pretty interesting. Like I said, I would keep your chemistry book if you plan on going into any type of medical field, because if you have to take organic chemistry, that's what the last chapter in this book is. And it's all these weird diagrams and all this stuff you have to do. So that might be a good reference book for you. If you have to go into any type of science field in college, you're going to have to take chemistry. So you might want to just keep your chemistry book just because of that anyway. Because sometimes, my kids, like my son, he's in chemistry right now, and they don't get a chemistry book. So sometimes he'll even look at my stuff just to say, how do I do this again? So you might want to just keep your high school books just as a reference for that, because even high school students don't get books now. So let's take a word of thanksgiving and praise and supplication to the Lord to help us, and then we'll start on our first section of chemistry. So Heavenly Father, we want to praise you and thank you this day for all the many blessings you've given us. And Father, please clear our minds, clear us from distractions, help us to learn what you would have us to learn from this section. And Father, help us to never be bitter or to become, feel like we shouldn't be learning things, because we know that whether it's in your word or whether it's an experience that happens to us, that the Holy Spirit placed that there for us and we're supposed to learn something from it. So we give you praise and honor and glory, and we love you. In Jesus' name, amen. So, oxidation and reduction processes. So we're going all the way back to chapter 4. In chapter 4, you learned a lot of chemical reactions. So, and you can look, we did a combination, we did decomposition, we had single displacement, double displacement. You actually had to categorize and match those as on some tests and some quizzes. But there's also another classification of chemical reactions that fall into one of two categories. It involves an electron configuration of the reacting substances So there's an electron configuration of the reacting substances, and there's also another ones where they don't react like that. So those in the very last one is what we're talking about. Those that do not make a configuration of electrons. Those in the first one, those that react with the, with those that make electron configuration with reacting substances is what chapter 16 is about. That's oxidation and reduction reactions. And just think, if you had to say oxidation and reduction, because they both take place at the same time, you would probably get your tongue into a big knot. So chemists just simply call it a redox reaction. So, and that's just where they take the first part of reduction and the first part of oxidation, and they just call it redox because they encounter at the same time. You in the lab have already encountered some laboratory redox reactions. You can probably remember I did a whole thing with my 7th and 8th graders last year on corrosion with nails. And remember, I left them there all year. And we just put nails in acetic acid and soda water and plain water. And those were galvanized nails, which we'll talk about later in this chapter, which they were not galvanized, sorry. They were supposed to, you can't use a galvanized nail would actually go over later on. And that was a redox reaction. That rusting that was taking place was a redox reaction. So there's all kinds of redox reactions that happen in industrial as well as just life processes. So let's talk about what is redox. What's a redox reaction? You're probably very familiar with the term of oxidation. If you think of oxidation, you probably think of my little thing that we did last year with my 7th and 8th graders, and that was those nails rusting or iron rusting. Another oxidation process is the burning of gas or oil. That's basically the reaction of a substance with oxygen. And while both of those processes are oxidations, one is slow, obviously, the nail took forever, and then one is pretty rapid, that would be the burning of gas or oil. Chemists generally use the term oxidation in a broader sense. Also, we use the word or the term, to get it scientific, reduction in chapter 11, where we discuss the production of metals from an ore. But there's lots of reduction reactions. They go back to I'm saying a lot. So they go back to a real general reaction that we've used just simplistically through a lot of things, and that is the reaction of metallic sodium with non-metallic chlorine, which I think is cool because sodium, potentially could blow you up, if it goes in water, and you probably wouldn't want to eat it. Chlorine, was actually used by itself. Chlorine gas was used as a poisonous gas in World War I. And you put these two seemingly weird substances and they combine into something yummy that we shake on our food. And it's been so important in our history time that Roman soldiers are actually paid their wages in this for the preservation of food. And that's sodium chloride. So basically you have two parts of a solid sodium, two molecules, of solid sodium, combined with chlorine 2, or two molecules of chlorine 2, that's a gas, and it becomes sodium chloride. In that process, an electron from that valence shell of sodium atom was transferred to the valence shell of a chlorine atom, which means each sodium atom lost an electron, each chlorine atom gains an electron. And this is what you need to know, is this next step. So I'm on the second column of page 268 underneath oxidation and reduction processes. Any process in which an atom loses one or more electrons is oxidation. So start highlighting this. Any process in which an atom loses one or more electrons is oxidation. Then keep highlighting. Any process in which an atom gains one or more electrons is reduction. And they give you a mnemonic device. Some of you like those, some of you don't. And it's Leo the lion says grr. So Leo stands for loss of electrons. That's oxidation. So, and gain of electrons is grr. That's reduction. You would think it's the same, it would be the exact opposite, but it's not. So the loss of electrons is oxidation. The gain of electrons is reduction. So the reactants in a redox reaction, like they explained with sodium chloride, may be viewed as acting upon each other to cause this reaction. One reactant is the oxidizing agent, and which causes oxidation by accepting electrons from the other reactant, and in that process it's reduced. The other reactant is the reducing reaction, which causes reduction by giving up the electrons for the other reactant, and in that process it's oxidized. Thus, in a redox reaction, the reducing agent's oxidized, and the oxidizing agent is reduced. And they give you a good analogy here. If you had a dirty sink or a bathroom, and you clean it by using some type of cleaner, Comet, bleach, whatever, in the process, the cleansing agent does the cleansing. So like your Comet, or your bleach is doing the cleansing. It's not getting clean. Similarly, the reducing agent does the reducing, but it doesn't get reduced. Rather, it's getting oxidized, and that oxidation, so that's it. Both of these happen simultaneously, so that's something else to learn just in your brain so you can get this out. Oxidation and reduction occurs at the same time, and that's one reason why scientists aren't bothered by just saying, hey, it's a redox reaction, because those are both happening at the same time. So whenever one substance loses electrons, some other substance must gain them. The electrons cannot simply disappear. That is, there's no oxidation without a reduction, and there's no reduction without an accompanying oxidation. So that term is just used as a redox reaction. That's why they use that. Now, in a simple reaction, like the sodium chloride one they did on page 268, it's kind of easy to see that there's been a change in electronic structure due to the transfer of electrons. But when you get, obviously, into more complex reactions, it's kind of hard to determine what's going on. So to determine what change in electronic structure has occurred in a reaction, scientists use signed numbers known as oxidation numbers. So let's look at this oxidation number. You kind of need to know what the oxidation number is, and then there's there's actually going to be a couple of questions that comes from oxidation, or the oxidation number. So the oxidation number of an atom is the charge of an atom. The charge the atom is assumed to have in a particular ion or a compound. And on your quiz, they'll give you some things and say, what's the oxidation number, or what's that? And that's why you kind of need to know, first of all, what the oxidation number is. So oxidation numbers are the result of assigning valence electrons to the more electronegative element involved in bonding, and that gives it a negative oxidation number. The less electronegative element is then assigned a positive oxidation number. So basically, what are oxidation numbers? They're a bookkeeping system. It's basically, for a chemist, it indicates a change in electron ownership for a chemist. It also permits a redox equation to be balanced more easily than it's possible just by looking at what's happening, and it may be used to predict the reaction of products and properties of a chemical compound, which is important for a chemist, not really so much for us. There's a bunch of rules. Your questions are going to come from the rules, but you still have to know the understanding of what an oxidation number is. So, let's start with Rule 1. The oxidation number of any element in its uncombined state is 0, and they basically explain. For example, chlorine is a diatomic molecule. Since both atoms in the bond are the same, each has the same pull, and then there's no reason to assign the electrons to either atom. So whether the element's monatomic or polyatomic, As long as one type of atom is present, it starts out with 0. Rule 2. The oxidation number of a monatomic or one atom ion is equal to its charge. And that's going all the way back over to the different ionic charges that we did way back in chapter 3 with stoichiometry. But that's okay. I'm telling you what charges you need to know here in just a second. Binary ionic compounds like sodium chloride and calcium oxide are composed of monatomic ions. Thus, in these compounds, and they give you the one you need to know, so start highlighting. The oxidation number of sodium is +1. That's really important. The oxidation number of sodium is +1. So make sure you highlight that. Then they give you chlorine, that's a -1. Calcium's a +2. Oxygen is a -2. Some elements form ions having different oxidation numbers. They give you sodium chloride, iron's +2, but sodium chloride is a +3. All of that we kind of covered way back when. Rule 3. Hydrogen has an oxidation of number of +1 in most of its compounds. So in most compounds, hydrogen has +1. The only exception is with metal hydrides, like lithium hydride, where hydrogen makes a -1. It's like, it's always true, unless it's not. All right, rule 4. You need to pick up on this one. Oxygen is assigned an oxidation number of a -2 in most of its compounds. So in most compounds, and for the purposes of high school chemistry, that's you. In most compounds, if I've got this big chemical equation and it's asking me what's the oxidation number of oxygen, it's telling me right here. It's a -2. So a -2. There are exceptions to the rule, like peroxide, and then they go over several other, or fluorine, oxide, or oxygen fluorine. But, for the majority of all the things you're going to have on your quiz, for this quiz, it's going to be a -2. Rule 5, halogens and their compounds are assigned an oxidation number of -1 unless they are bonded to a more electronegative halogen or to an oxygen. Rule 6, and what you can see, guys, is they're going across the periodic table, all right? They're just kind of going, they're doing a bookkeeping as they're going across the periodic table with these redox reactions and giving them oxidation numbers. So alkali metals, group 1, alkaline earth metals, group 2, and aluminum, which is group 13, and their compounds have a positive oxidation number equal to the number of valence electrons in that neutral atom. So they give you an example, potassium. Potassium in any compound is always +1. Potassium is +1. Calcium is +2. And if you can remember what we did with, I'm trying to look up here. So it's equal to their valence electrons there. You can kind of see what the valence electrons were given to you on your periodic table. Moving to Rule 7. Rule 7 is basically the algebraic sum of the oxidation numbers of all atoms in a molecule or polyatomic ion must equal the charge on that particle. Once again, this is high school algebra. We're not getting into this seriously in depth. They do explain it to you very well and in depth. And if you were here, we might go over it more. But since you're not, that's basically what you have to know. They gave you a summarization of the rules on page 16.2. I told you which two, that you have to understand what oxidation numbers are. Then there's 2 that you just have to. They're going to give you a chemical equation. They're going to ask you, hey, what is the oxidation number in this chemical equation? And if it's sodium, it's +1. If it's oxygen, it's going to be -2. So now let's move over to, I'm trying to see if we've got, what did I get to? Nope, we're not quite there. So, oxidation numbers in redox reactions. They've given you lots and lots of examples. I'm going to try to go over what you would need to know with each little section. We're not covering each thing here because even when I looked on your test, they really didn't. They give you a lot of information right here. That's why you might need it for college chemistry, but they're not using it in your high school chemistry. But they give you a lot of explanation for it, so it might be good to keep this book. So under oxidation numbers and redox reactions, when an atom loses electrons or it's oxidized, the charge on the atom becomes positive or more positive. Therefore, this is a little thing you need to know just for your understanding. Oxidation is a process in which the oxidation number increases or it becomes more positive. And then in the same way, reduction or the gain of electrons is a process in which the oxidation decreases or becomes more negative. And to keep those processes straight, remember that reduction is a decrease in the oxidation number of an element. Then they go over sodium chloride, they go over some thing with zinc, just showing you that process in a chemical equation form. I'm not going through that. But like I said, you might need this in the future. Moving over to page 271, they're showing how you use oxidation numbers in order to balance a redox equation. You don't, even if we were here and we were doing this on a test, they don't require you to do this on a test. There's just a few things they wanted you to recognize. So up to this point, we've balanced equations by inspection, but we balanced really simple ones. So the main thing here is to understand is everything you've done with balancing equations, as complex as it seemed to you, is really not as complex as it actually was. That's what I think you need to gain. Unfortunately, many redox equations are very difficult to balance by inspection because of the number of terms involved. So an oxidation number provides a different, less complicated method for being able to balance a redox equation. So the method here, and I just want you to, I'm not going over 1 through 8, but basically, in a balanced redox equation, the total decrease in oxidation numbers must equal the total increase in oxidation numbers. So in a redox equation, it has to balance. The total decrease in oxidation numbers must total the increase in oxidation numbers from one element to the other. If you want to read it and balance some equations, you've run out of Netflix, you've run out of YouTube, knock yourself out there. So let's turn on over to page 272. And this is where they're going over the strengths of oxidizing and reducing agents. There is a quiz question from this section. So let's read over it. I could not really find where your quiz question was just where it was just given to you straight up with words. So we're going to read it and then I'm going to go over it a little bit. So as you work with redox reactions, you might notice that several elements or ions occur in the role of reducing agent or oxidizing agent more often than others. And they're just talking about how zinc commonly acts as a reducing agent, whereas a halogen and the permanganate ion commonly act as or magnesium oxide is what that was, commonly act as an oxidizing agent. Zinc has a relatively large tendency to just give up electrons. Zinc just can't hold on to it. We've actually performed an experiment where we put zinc in silver nitrate, I believe is what it was. We put zinc in silver nitrate, and the zinc would actually, or maybe it was copper. Maybe it was a copper wire. I was thinking it was zinc. It might have been something else. And when we did that, it actually just it started trying to really pull the silver from the silver nitrate on it. Remember, we had that little furry piece of metal. So zinc has a relatively large tendency to give up electrons or become oxidized, so it's a good reducing agent. Magnesium oxide contains manganese and the +7 oxidation state, so it has a tendency to become reduced and serves as a strong oxidizing agent. And then they go over some other strong ones. So a strong oxidizing agent readily acquires, not requires, electrons in a redox reaction to be changed into a form that is a weak reducing agent. So, they give you a table here that shows you this. So a strong reducing agent, like an alkali metal or zinc, readily loses electrons and is changed into a weak oxidizing agent. That's reasonable, that just happens. It's reasonable since a substance with a large attraction for electrons will not, or a strong oxidizing agent will not readily give them up, like zinc. So they've given you some of the strengths. Here is your quiz question where, once again, I can't find where it's just spilled out. So you might want to just write this out as I say it. So redox reactions, and it's kind of like, this is a quiz question you have gotten from reading this whole first section, and then they want to know that you understand this. It's a cognitive thinking. Like, I read the whole first thing, and this is my cognitive assumption I got. Redox reactions tend to occur in the direction that produces a weaker oxidizing reducing agent. So whichever one's weaker. Redox reactions tend to occur in the direction that produces weaker oxidizing and reducing agents. It could be, in one, it might move to the weaker oxidizing agent. In the next reaction, it might move to the weaker reducing agent. That's the direction it moves in, whichever one is weaker. You have to know that cognitively to be able to answer it. I can't remember, it's a fill in the blank. It's either, question. But redox reactions tend to occur in the direction that produces weaker oxidizing and reducing agents. So if you notice, that's moved us over to page 272. We're not doing homework. So all you've got to do is that quiz, the quiz will come to you on April 27th, and that's your last quiz. It is over the most of the majority of the chapter, so we'll continue going over some things. So on Monday, we'll start going over 16.2. So have a great weekend, and I will see you on Monday, which I might be filming this today, so I might see you later today. Have a great day. See ya.